In the previous section, we introduced uniform circular motion, where an object is moving on a circular path at constant speed. And although the speed of the object is constant, its velocity is not, as it continuously changes direction as the object moves around the circle. Since the velocity is changing, the object is accelerating. Notice in the figure how the velocity vector has different directions at different times. We might have guessed that an object moving in a circle must be accelerating, since Newton's first law tells us an object will continue to move in a straight line at constant speed unless acted upon by an external force, and thus an acceleration. The acceleration responsible for circular motion is called centripetal acceleration. Let's determine how to calculate the centripetal acceleration for an object moving with speed v along a circle with radius r. As always, acceleration is defined as the change in velocity divided by the change in time. The figure shows two velocity vectors of the object at its initial position at time t initial and its later position at time t. During this time, the object sweeps out an angle theta. As long as we don't change the length or orientation of a vector, we can slide it around our figure to better illustrate the vector subtraction of v minus v initial. Remember that vector subtraction is really just vector addition, where v minus v initial is equal to v plus negative v initial. Notice the vector negative v initial is equal in length and orientation to v initial, but it points in the opposite direction. We now slide negative v initial down to vector v in order to add them together. Since the two vectors are drawn tail to head, the resultant vector delta v is drawn from the tail of the first vector to the head of the second one. The direction that delta v points will correspond to the direction of the acceleration. Here we see that delta v points in toward the center of the circular motion, and so does the centripetal acceleration. In this simple illustration, we have assumed that theta is small. In other words, we are considering the motion of the object in the limit that delta t approaches zero. Thus, we are calculating the instantaneous acceleration of the object, or the acceleration of the object at any time, which will always point in toward the center of the circular motion. This takes care of the direction of the centripetal acceleration vector. To see how to calculate its magnitude, we can compare two similar triangles. Let's look at the section of arc swept out by the object as it moves from its initial to final position. We can call this arc length distance s, and it must be equal to r times theta. There is also a straight line distance between the initial and final positions that we'll call s prime. But in the limit that delta t approaches zero, and thus theta is small, s prime will be equal to s. Thus we end up with two similar triangles, one from the subtraction of the velocity vectors we did previously, and this one from looking at distances. The ratio of congruent sides of similar triangles must be equal. Therefore, delta v over v must be equal to s prime over r. Furthermore, s prime is the linear distance covered by the object, which is just equal to its speed, v, times the time interval delta t. We can now rearrange this expression for delta v over delta t, which is the acceleration of the object. Notice it is equal to the speed squared divided by the radius of the circular motion. This is how you calculate the magnitude of the centripetal acceleration, or a sub c. And the direction of the centripetal acceleration vector will always point in toward the center of the circular motion.